and we're kind of combining a couple sections here because of the nature of our courses being online and not as much time to really get things done in the detail we'd like. So we're kind of going to condense section 3.1 and 3.3 here and cover a little bit of both. But here's this problem. It says determine the intervals on which f of x is increasing and decreasing. And the textbook gives you a picture. And so what I did was I've gone to desmos.com, a great graphing utility, and input the equation f of x, negative, parenthesis, x plus 1 squared, and just took a quick screenshot and dropped it in here to Google Docs so you can see the graph. And what we want to do here is we can figure this answer out by just looking at the graph, and then we're going to verify it through calculus and algebra. So very quickly, we can take a look at this. If we remember from back in algebra, we know that this is in vertex form. Vertex form, we could see that our x value, our vertex is shifted plus 1 means 1 unit to the left. We don't have an addition or subtraction outside the parentheses, so that tells us a vertex has not shifted up or down. So we know that our vertex is going to be at the point negative 1, x for the x value, and 0 for the y value. So we know that, so we might as well write that down. Vertex equals negative 1, 0. Okay, so just by taking a look at this, we can see you're tracing the graph. As we move along this graph, think about what's happening to your y values, your value of your function f of x. When we talk about intervals on which f of x is increasing, they're f of x, y equals f of x. So we're talking about when is the y value increasing. And as we trace the graph during this section, our y value is starting at a negative value and moving upward. Our y value, our function value, is increasing. And when is it increasing till? Well, until it hits this vertex. So we can label that as increasing on the interval, and we're going to use a parenthesis. Keep in mind, your parabolas continue to expand to the left and the right infinitely. So we are actually increasing from way, way out here to the left at negative infinity. So we would want to actually put in here, let's see if we can insert a symbol here. Special characters. And I know I've done this before. Nope. Number, maybe under number. All right, well, I don't see it, so I'm just going to type in the word infinity. From negative infinity. And it is going to continue increasing until it hits an x value of negative 1. Once we get to this x is negative 1, the vertex here, our y value begins to decrease, and it's going to decrease on the interval, parenthesis, from negative 1 to positive infinity, because that graph is going to continue to expand to the left and the right infinitely. So we can see here, why do we use parentheses? Well, we use parentheses for infinities all the time. And we use parentheses on the negative 1 values here in our interval form because at the point negative 1, 0, at that instant it is not increasing or decreasing. We're going to talk about that in just a second. That is, as we talk about the calculus, that is what we refer to as a critical value of our function, or a critical number of our function. So here we go. We've got our increasing, decreasing intervals, and we've got them from the picture. And that's great because we have an easy equation that we could very easily graph. Won't always be the case. Let's go ahead and move down here to the bottom where we have a little more room. And we're going to bump this up a little bit for an equation. And we're going to put in our equation as f of x equals negative parenthesis x plus 1 close parenthesis squared. And so now we're going to do this using calculus. And here's the most important thing we have to find here is we've got to find something called a critical value. And critical values are anywhere that your derivative equals 0. Maybe we should label this. Anywhere the derivative is equal to 0, anywhere the derivative does not exist, and in some circumstances you might have endpoints or interval values for your function, and those are potential critical values, so we'll say endpoints if given an interval, which in this case we were not given an interval. Okay, so what we want to do here to find critical values are anywhere the derivative is equal to 0, we're going to need to take the derivative of our function, and then we're going to set it equal to 0 and solve it. So, very easy derivative here because we're going to just do a quick chain rule on this. F prime of x is equal to, remember chain rule, exponent times our coefficient, that's going to give us -2. The inside stays the same, x plus 1. Subtract 1 from the exponent, 2 minus 1 would give us an exponent of 1, which is unnecessary to write. Now we've got to multiply by the derivative of the inside, and the derivative of x plus 1 would just be 1. And if we simplify that down, the multiplication by 1 is irrelevant, the exponent of 1 is irrelevant, we have -2x minus 2 if we go ahead and distribute our -2 value here. So that's our derivative, and we want to know when will that derivative equal 0? Well, that's a very simple solve. -2x minus 2 equals 0. Very simple solution. We're going to add the 2 to the other side. That's going to give us -2x equals +2. We're going to divide by a coefficient. So what are we going to end up with here? Let's get out of there. We're going to end up with x equals -1. And that's our critical value. So there's an easy trick for us to do here. I'm not the best at drawing on these. I know there's a menu to do it. But the bottom line is this, is we want to create a number line essentially, or what we would call is an x-axis. And we want to think to ourselves, okay, if we put this critical value on the x-axis, this becomes a partition. It's going to separate our, oh, here we go, let's see if we can do this. It's going to separate our number line into different pieces. I'm going to draw a line, we're going to draw it from here, right across to here. Wonderful. We want to do a simple scribble right there, great. Do another one. This is going to be the value of I don't know why it didn't draw that for me. Just put a text box there and try that. That's the value of -1 on our number line. Okay, so this is going to separate our value or our graph into two different partitions. The part of the graph that's to the left of -1, the part of the graph that's to the right of -1. So what we want to do next is we want to pick a number to plug in from each interval. So let's pick a number here, -2. And we're going to pick a number here text box. Remember over here, and it's always easy if you could pick zeros and ones. So I'm just going to pick 0 because that's going to be easy to plug in. So what we're going to do is we're going to take this -2 value and we want to plug it into our derivative. So we want to think here. All right, what would f prime of -2 be? That's not what we want to do. Go down one. Sorry, this is a little new. There we go, new equation. We want to figure out what would f prime of -2 be equal to. Well, plug -2 into your function. -2 times -2 is +4. +4 minus 2 gives us a +2 as a result. Now, why is that significant? Well, remember, derivative means slope. So when we plugged in a numeric value over here to the left, we got a positive slope out of our derivative. Positive slope would mean our tangent lines would be positive lines. So anywhere there is a positive slope, that tells us that our function, f of x, is increasing during that part of the graph. Okay? Using up so much space here. Back that up one so I can fit one more line in here. Second, we want to plug in this value. So we're going to f prime of 0 equals. So let's plug in 0. 0 times -2, 0. 0 minus 2, that's going to give me -2 as an answer. That means that during this section of our graph, all of our slopes of our tangent lines are going to be negative. Well, look at it. Yeah, anywhere over here we drew a tangent line would give us a downward slope or a negative slope. So anytime we get this negative slope output, that tells us that f of x is decreasing. So that's what we really want to look for here. We want to try and find these critical values where our derivative is equal to 0. We want to put those on a number line, and that partitions our domain into separate groups. Then you're just picking a test number from each group and plugging it into your derivative. Positive outcomes tell you your function is increasing during that range. Negative outcomes tell you your function is decreasing in that range. I hope this helps. I know it was a whole lot going into this, and we're going to do some more examples shortly. So if you still have questions, hold tight. We'll try and get some more examples up later in the day.